Good to go there, Dave.
Okay. The link for me to, oh, there we go, there's record, here we go. Good evening, ladies and gentlemen, and welcome to Ireland. We're delighted this evening to have Professor Dan Tovey, who's going to talk a little bit about what's been going on in astronomy in Ireland, and then our main getting huge.
Dave, your audio's dropping. You're just going to have to go ahead with Dan.
Sky at night on BBC tonight. It really is that bad, yeah?
Yeah, it's really bad.
Actually, a full signal, I don't understand it. Right, well, look, we'll try and fix out the tech, and if people can hear me, over to you, Dan.
Okay, thanks very much. Can people hear me okay?
Do you mind introducing yourself, if you can hear me?
Yeah, sure. Can people hear me okay?
Yes.
Yeah, great.
Can.
I'll go ahead then. Yeah, so my name's Dan Tovey. I confess I'm not an astronomer. I'm actually a particle physicist, so maybe you'll be getting something slightly different tonight from me. The topic of my talk tonight is on dark matter searches. As I said, I'm a particle physicist. I work at the University of Sheffield in the UK. I've worked for probably half my career on dark matter searches in one way or another, and then the other half I've actually been working on the Large Hadron Collider at CERN in Geneva. And actually these two topics are connected, so I hope to tell you a bit about that tonight. So what I'll do is I'll share my screen now, if I can. So just, okay, can people see that okay?
Yeah, perfect.
Fantastic. Okay, so I will get going. So yes, the title of the talk is Astrophysics Underground, Terrestrial Searches for Dark Matter. And really the focus of the talk is an overview of efforts to identify the nature of dark matter through measurements carried out on Earth. So this isn't really going to be a talk about sort of cosmology or the theoretical motivations for dark matter. I will touch a little bit on motivations for why we think it's out and how we search for it, but the main focus will actually be on measurements and experiments that we can carry out on Earth to try to understand what the dark matter is. It's a very big topic. In an hour, I can't really hope to go through the full breadth of what we're going to be what we could potentially be looking at. So I've got to make a few choices. So I'm going to focus on one particular class of dark matter particle candidate, so one particle that people think might constitute the dark matter, which are called WIMPs, or weakly interacting massive particles. So I'll explain what WIMPs are, and hopefully you'll get a feeling for how we go about searching for them. I should say on some of these slides, there's a reasonable amount of detail. I won't go through all of that detail in the talk, but if you'd like further information, then just ask me at the end, and I'm happy to answer any questions that you might have. Okay. So first of all, what is dark matter? Well, I guess since you're all interested in astronomy, you will probably have heard of dark matter. It is believed to make up 23% of the mass energy budget of the universe. So up until probably the mid-90s, we thought it was probably an even larger fraction than that. We now know there's the majority of the mass energy budget of the universe is made up of dark energy, which is a whole different subject, and I won't be saying anything about dark energy here. But 23% is dark matter, and only a very small fraction, down in the sub-percent levels, is matter that's in the form that we're sort of familiar with in terms of stars and the kind of things that we can observe with normal telescopes. So there's this large amount of matter in the universe that we really have no idea what it is whatsoever. And so that's really one of the most pressing questions in modern science, really, is to understand the nature of dark matter. So quite often when we talk about dark matter, we go through the sort of historical evidence for dark matter. I will be saying a little bit about the history, but I'm going to take a slightly different approach here. I'm going to look at dark matter on different scales. So as you know, when you look through a telescope, you can look at objects which are nearby, moon or the planets, or you can look out on larger distant scales out at galaxies or even structure in the universe. So I'm going to start at the very largest scales, and there we have measurements of the cosmic microwave background radiation, which sort of leaves and has imprints on it of structure in the early universe, structure of the early universe. And we can compare those measurements with what we really is our sort of default model now for the evolution of the universe, sometimes called the lambda CDM model. Lambda means refers to dark energy, and CDM stands for cold dark matter. So measurements of the cosmic microwave background from missions such as COBE, WMAP, and most recently the Planck satellite, have measured really with incredible precision the fraction of the universe that is made up of different components. And from that, we know that the amount of the universe that is in the form of cold dark matter, CDM, is basically 26%. You can see the number there, 0.259 is the fraction, plus or minus 0.006. So it's really well measured, actually. It's a very well understood number, but we have no idea what actually that stuff is. What we do know is cold dark matter, CDM, is what we say it's non-relativistic at freeze out. And I'm going to say a bit about what that means in a few slides' time. But what this means is that the structure in the universe, if the universe is dominated by cold dark matter, small scales. And from that, actually, we can constrain whether dark matter is in the form of cold dark matter or hot dark matter, which is typically in the form of much lighter fundamental particles, where the structure in the universe grows from large to small scales. So we have a pretty good idea that the dark matter in the universe is what we call cold dark matter, but we don't know actually what it is. So what else do we know about it? Well, this sort of complicated plot you see on the right here, I'm not going to go through that, but I can explain it to you if you're interested. But there is a very successful theory called Big Bang nucleosynthesis, which makes predictions for the amount of the light elements that were produced in the Big Bang, in the early universe, as a function of a quantity called the baryon to photon ratio. And if we use our measurements of those abundances of the light elements that we can measure with astronomical satellite missions, telescopes, we find actually that we can combine those measurements with the theory of Big Bang nucleosynthesis to make a prediction for this baryon to photon ratio number. And independently, we can measure that number with the cosmic microwave background missions that I mentioned on the previous slide. And if you look on the right-hand plot, you'll see that the vertical bar, the pink vertical bar, is the prediction from Big Bang nucleosynthesis, and the blue vertical bar is the prediction from cosmic microwave background. You see they lie right on top of each other. And they're also roughly internally consistent. There's a few issues with the abundance of lithium-7, which is a light element that's produced in the early universe, but that may have some uncertainties that are misunderstood at the moment. The reason I'm telling you this is because this is basically evidence that we understand really well the evolution of what's called baryonic matter in the early universe. So that means nuclear matter, the matter that's all around us, that makes up the world around us. And that basically tells us that the majority of dark matter is not baryonic. It must be non-nuclear matter. It must be something that is not what we observe today around us. So that probably means that it's a new kind of elementary particle. And that's why the search for dark matter becomes something that particle physicists might be getting interested in. So then moving down to smaller scale, we look at clusters of galaxies. And again, I'm not an astronomer, so I don't pretend to know all the ins and outs of this, but various different techniques looking at, for instance, the motion of galaxies in clusters, or using gravitational lensing of light, which is something predicted by general relativity, Einstein's general relativity. We can map out the amount of dark matter in clusters. And the picture you see here is of the bullet cluster, which is sort of the classic example of where here we've used gravitational lensing to find strong evidence that basically the majority of the matter in this cluster is in a place where basically there's very little baryonic matter, very little stars or hot gas, which again tells you that it's something else that's providing the dark matter. So then, if we go to smaller scale still, and we look at galaxies, inside galaxies now, we also find evidence for dark matter. And this is really the classic example that if you've ever heard anything about dark matter, this is probably the case that, you know, the evidence that you most commonly hear about. It's called, they're called galactic rotation curves. And they're basically, that's a sort of jargonistic term. It just means you look at the velocity of stars and gas rotating around a spiral galaxy as a function of the radius out from the center. And if you look at the plot on the right, if you look at the yellow points, you can see that they rise from the center. And then they carry on rising, and they carry on, the speed of rotation carries on rising right out to the furthest edge of the stars in the galaxy, the furthest stars from the center of the galaxy. You can still measure rotation velocities from hot gas, even at larger radii, and that's the blue points. And you see that basically the rotation velocity is still increasing at large radius. And this presents a problem if you don't have dark matter, because in a galaxy, all the visible matter, or the vast majority of the visible matter, is held in the core of the galaxy. So to a good approximation, you can assume that once you're outside the core of the galaxy, there's no more matter to provide any gravitational pull. And if that's the case, then basically the rotation velocity should fall off like 1 over the square root of the radius, which is what we see as the dashed line. Clearly, that dashed line is very different from the full line, which is sort of what is fitted through the points that you see. And that is actually, that full line is generated by assuming that there's, in addition to the visible matter, there's a spherical, what we call a halo of dark matter, invisible matter in a sphere all around the galaxy, which is providing some extra gravitational pull to keep the stars and gas rotating at larger and larger velocities, or at least constant velocity, as we go out to very large radius. So that's evidence that there's dark matter in galaxies, not just on larger scales, but on the scale of galaxies. And that's very important for efforts to try to detect and understand it. So if dark matter is trapped in galactic halos, and in fact, what we observe is the highest densities of dark matter are trapped in galactic halos, then that's beneficial for dark matter searches, because that potentially means that if we put a a specialist dark matter detector on the Earth, then it may be that dark matter passing through the Earth might interact with that detector. And so that's one way of searching for dark matter. There are other ways. You could use remote measurements looking for annihilation or decay of dark matter particles elsewhere in the galaxy using telescopes. That's another possibility. I won't be saying anything about that, but what we typically call direct detection is looking for interaction of dark matter particles inside a detector on the Earth. Now, to interpret and predict what signals we should see, you need to understand what the dark matter is doing in our galactic halo. And so we make some assumptions. They're reasonably well motivated. We basically assume that the dark matter actually behaves like what's called a collisionless gas, which is basically they're all the dark matter particles are all moving around inside the potential well of our galaxy in much the same way as a gas, basically. And we, given that we know the size of the potential well of our galaxy, we can make some reasonably good assumptions about the speed that those particles are moving at. It's typically something like 220 kilometers per second on average. There are some other advantages of searching for dark matter on the Earth to do with the motion of the Earth through the galactic halo. I'm not going to say anything about that, but if you're interested, there is a way to effectively do astronomy with dark matter searches, which effectively building a telescope. But I can say more about that at the end if anyone's interested. Okay, so what are the dark matter candidates? Well, there's a huge range that theorists have come up with, and somewhat amusingly, I would say, whenever particle physics theorists come up with a new theory of particle physics, it's almost guaranteed that that new theory will come up with a dark matter particle candidate. So the theories may be proposed for some completely different purpose, to solve some other problem in particle physics, but usually those theories also have a dark matter candidate, because it's really the one clear piece of evidence we have that there is new particle physics out there in the universe that we don't really understand. We know that dark matter must be weakly coupled to normal matter, to baryonic matter, nuclear matter, basically because we don't observe it forming heavy elements. You don't see strange elements trapped in rock or on the Earth, which are anomalously heavy because they've got a dark matter particle stuck to them. So we know that it couples weakly. In this diagram, there's a whole pile of possible candidates, and I'm just going to talk about the red area on this diagram. This is an energy is plotted along the horizontal axis. And I'm going to talk about WIMPs, weakly interacting massive particles, which are typically in the units we use, MeV to GeV to TeV range. Just to briefly say, why are we interested in WIMPs, weakly interacting massive particles? Well, it's a catch-all term, but it has some very nice property. WIMP candidates have a very nice property, and that is that in our theories of the very early universe, soon after the Big Bang, the universe existed as basically a ball of hot plasma, and that plasma was in what we call thermal equilibrium. It means that all the time, particles, not just dark matter particles, but everything, normal matter around us, was being created and destroyed in equilibrium. And as the universe cooled after the Big Bang and expanded, eventually there came a point where it was sufficiently cold and underdense that this annihilation process could no longer take place. That's what we call freeze out. And that constrains a lot of the theories of dark matter. And an interesting observation is that for the kind of densities that we observe for dark matter today, about 30% of the universe, the natural mass of the dark matter particles is around what we call the electroweak scale. And that's something that comes from particle physics. It's connected with the physics of the Higgs boson, if you've heard of that, and the origin of mass in the fundamental particles of the universe. So there may be a connection there between dark matter and really fundamental particle physics of the Higgs boson, which would be a neat idea if it were true. And that's one of the reasons why we're interested in these WIMP particles, because they have that property. Okay, so how do we go about searching for dark matter? Well, there's three main ways. I mean, I'm not considering the gravitational searches for dark matter here, which what I've just talked about, because that doesn't tell you anything about what the dark matter is. It can tell you that it's out there. It doesn't tell you anything about what it is. To understand its nature, you have to see some different interactions of it. The three ways is direct searches for dark matter, which I've touched on briefly already. Here you look for evidence of dark matter particle interactions with targets in terrestrial detectors. These targets could be nuclei, atomic nuclei, protons and neutrons, nucleons inside the nucleus, electrons, photons, so light effectively. So they can prove that if we see a signal there, that we are looking at that dark matter is indeed in the form of particles. It doesn't actually identify directly what the particle is. It gives us some evidence, not directly. Another thing we can do is look for evidence of the production of invisible particles in particle collisions in particle accelerators on the Earth. And if I have time, I'll touch on this at the end of the talk. If we can produce dark matter in a particle accelerator, that might well identify the particle through the experiments we can carry out. It doesn't actually prove that it's dark matter, because of course, if we produce a particle, it could then decay to something else soon after we produced it, and that lifetime is probably going to be a lot less than the lifetime of the universe. So it might not be dark matter that we've observed, but it could be. So it's interesting evidence. And then what I won't say anything about is indirect searches, which I mentioned earlier. This is where you're looking for annihilation or decay of dark matter particles trapped in galaxies, stars, or even in our own planet. So these are the three techniques, and I'm going to talk about the first two. So I'm going to touch on direct searches first, and I'll explain a bit later what this rather impressive picture represents. So direct searches for dark matter, this relies on an idea which really was proposed in the early 80s, which is that if we have WIMP dark matter particles in our galactic halo, they may well pass right through the Earth, hardly ever interacting, because they're weakly interacting. But just occasionally, they might interact with an atomic nucleus. Very, very rarely, but sufficiently commonly that we might actually be able to observe it happening. So, for instance, a dark matter particle, a WIMP, could interact with, for instance, an atomic nucleus. And if you look at the diagram on the right, there's sort of the arrows coming in, the arrow on the left coming in is a dark matter particle coming in, it's hitting an atomic nucleus, and it's recoiling, sort of like a billiard ball or pool ball. And it's what we call elastic scattering. So given that we have a reasonable idea about the speed of the dark matter particles in our galactic halo, so it's about 220 kilometers per second, we can work out roughly what the energy of the recoiling nucleus will be after it's been struck by a dark matter particle. And that energy is typically something like 25,000 electron volts in the units that we use to measure energies in particle physics. That's a very low energy, incidentally. It's very difficult to measure energies that are that low. Now, we have to worry that there are other processes that can also cause things to recoil through normal matter. Dark matter particles can scatter off nuclei, but equally, we can get electrons in atoms also recoiling. And that's generally due to either beta decay, which is a nuclear decay process, or from Compton scattering, which is where a gamma ray in the environment around us comes in and scatters off an electron. If there's radioactive contamination in our materials, that can cause electron recoils. So we have to do something about that, and that actually drives a lot of the design of these experiments, these dark matter direct detection experiments, is minimizing this electron recoil background, as we call it. So in other words, things which are recoiling through materials with some energy, typically of order 25,000 electron volts, but which are not nuclei and are not caused by dark matter scattering. There are other processes which can also cause nuclei to recoil as well, though. For instance, neutrons, which are present all around us, for instance, from cosmic rays hitting our environment. There's neutrons going through me at the moment, coming from cosmic rays, also from radioactive contaminants just in materials all around us. There's always radioactivity all around us. So we need to eliminate all of these background processes. So how do we do that? Well, so we have electron recoils, nuclear recoils, and if you look at the right-hand plot here, this is a typical energy spectrum of the recoiling objects, be that nuclei or electrons or whatever, in a particular piece of material. I won't say what that is yet, because I'm going to come on to that. But you can see here, if you look at along the x-axis, the horizontal axis, you can see this is the energy of the recoils. And on the y-axis is the rate, basically, of which they occur. Now, we're interested in the very lowest energies. Don't forget, I said 25 keV. So if you look on that horizontal axis, 25 keV is right down at the left-hand end. So down there, the dominant background is this blue curve labeled 222 radon, Rn. And that's actually electron recoils coming from the decay of beta decay, nuclear decay of radioactive nuclei produced by radon decay. Some of you may know a bit about radon. It's a particular worry in limestone areas. You get a lot of radon emitted. It's actually a health hazard. I know that in Ireland, there's in the sort of karst areas and in the limestone areas, you get a lot of radon emitted. This is the same thing. This is a problem also the dark matter searches. So how do we get rid of these background processes? If we want to see dark matter induced nuclear recoils, we need to get rid of all these other processes. So the first thing we can do is make our target that is going to be struck by the dark matter as pure and free of any radioactive contamination as possible. So pure target and detector materials. We then need to shield that with various materials that will absorb any radioactivity or radiation which is likely to come in from outside. And for that, we can use lead, copper, water. Then we can stick the whole thing deep underground, and that will shield out cosmic rays. And as I said, cosmic rays can create neutrons, and we don't want neutrons because they can create nuclear recoils that look exactly like the dark matter-induced recoils that we're interested in. So we want to operate our experiments deep underground. And finally, we want to be able to identify whether what we're looking at is a nuclear recoil or an electron recoil. And for that, we need some really fancy physics, actually. So how do we identify electron recoils and reject them. Well, the way we do it is we build a dark matter detector made of a particular material, which typically emits two different signals as a result of a recoiling nucleus or electron going through it. So those signals could be heat, they could be electric charge, or they could be light. And I'm going to be talking about experiments that use charge and light. The sort of the words you can see on this diagram, the strange words you can see, they're all names of experiments. And I'm going to be talking about one called LZ, which if you look at the bottom middle, you'll see there's an LZ. It's an American experiment, so or it's based in America, so LZ. And that looks at charge and light. So how do we use this? Well, this is a liquid xenon detector. So if you've ever had a car with a very powerful headlight, perhaps a bit old-fashioned now because we tend to use LEDs for everything, but perhaps 10 years ago, a lot of people use xenon headlamps. So that's xenon. So we use liquid xenon. We cool xenon gas down to about 160 Kelvin, and it liquefies, and we can purify it, make it very, very clean, very little radioactive contamination. And it has a nice property that when a nucleus recoils through it, it generates a flash of light. And we call that flash of light the S1 signal. And we record the S1 signal, it's called scintillation light. We record it with light detectors called photomultiplier tubes at the top and the bottom of the sort of pot of liquid xenon. However, in liquid xenon, another nice property is that the recoil also generates some electric charge, some ionization. And what we do is we put a big electric field through our pot of liquid xenon, and in that electric field, the ionization, the electrons that are liberated by the recoil, they drift upwards into a region, which is called the electroluminescence region, where they create another flash of light. So we get two flashes of light. The second flash of light is called the S2 signal. And quite nicely, we can use the time difference between those two signals to work out the depth in the pot of xenon where the interaction occurred. So we know the position in vertical distance. And then from the pattern of light that we see in the photomultiplier tubes, we can work out where it is, where the signal was in the horizontal plane. So we can basically locate, or in the jargon we use, fiducialize the interaction using the signals. So that's one neat property of liquid xenon. It also has some other advantages. It's very radio pure, has very little radioactive contamination in. It's a heavy nucleus, which means that it hopefully interacts more strongly with dark matter particles than lighter nuclei. It's quite a well understood technology. We've been building experiments with liquid xenon for probably 30 years now. And above all of these, the really most important property of liquid xenon is that we can tell the difference between an electron recoil and a nuclear recoil. So we can tell the difference between background recoils from electrons and signal recoils from nuclei, possibly from dark matter scattering. How do we do that? Well, I mentioned these two light signals, the S1 signal and the S2 signal. If you plot them against the S1 and the S2 against the S1, the size of the S2 signal against the size of the S1 signal, for each recoil event, as we call it, each recoil, what you see is actually that the ratio of the two numbers, or relative size of the two numbers depends very strongly on whether it's a nucleus that's recoiling or an electron. So if you look in this plot here, the orange points are nuclear recoils. So they are what dark matter interactions would look like. And the blue ones are electron recoils. And you see, they don't lie that much on top of each other. They're reasonably well separated. So in other words, if you see a recoil that sits in the orange region, then that's pretty good indication that you're seeing nuclear recoil. And that might well be due to dark matter scattering. Okay, so what is LZ? It stands for Lux Zeppelin. I won't go into the historical reasons behind that. But basically, it consists of a big pot of liquid xenon at the center of the experiment. It has a mass of something like 7 tons of liquid xenon. And then surrounding that is a what's called a Veto Detector, which is basically made of something called a liquid scintillator, which is basically effectively an oil that also scintillates. It also gives out light when radiation interacts with it. And so what we look for are interactions in the liquid xenon that do not also generate a signal in the Veto Detector, in the gadolinium loaded liquid scintillator outside, because that, if we had a background process, that might well interact in both detectors at the same time. So we look for signals which just occur in the central liquid xenon volume. Outside the Veto Detector, we then have a water tank, which then absorbs and shields the detector, absorbs radiation that's coming in from outside the experiment. And inside this detector, we have, as I said earlier, we have these photomultiplier tubes, which are very sensitive light detectors. We have some in the center of the experiment, which are above and below the pot of liquid xenon, and they're recording the light from the liquid xenon. And then we have other ones which are inside the Veto Detector, or inside the water tank, which are observing the scintillation light from the gadolinium-loaded liquid scintillator in the Veto Detector. So we use a lot of these photomultiplier tube devices. This is the Lux Zeppelin collaboration. It's primarily US institutes with quite a few from the UK, including Sheffield, where I'm based, and one in Portugal and one in Korea as well. The experiment itself is based in the Sanford Underground Research Facility, SURF, which is in South Dakota in the United States. You can see a picture of the sort of the surface of SURF. It used to be an operational gold mine. It's called the Homestake Mine. And in fact, its history of use for physics goes back a very long time. And in fact, it's already had 1 Nobel Prize awarded for work done there, but to Ray Davis, looking at neutrinos. So, which is another sort of elementary particle. So the advantage of the Homestake Mine, of SURF, is that it's very, very deep, as you can see, the bottom right-hand plot. This is showing as a function of the depth measured in some standard units called meters water equivalent. It measures the flux of cosmic rays, cosmic ray particles called muons. Because SURF Homestake is so deep, we have a very low flux of cosmic rays, which is good for a dark matter experiment. So this is the water tank that I was mentioning. The outside of the water tank, inside the Homestake mine, so you can sort of see the rock walls covered in shotcrete on side, which sort of keeps everything together. So this is deep underground. And then here you can see the construction of the LZ detector. So what you're seeing here is, I didn't have time to discuss it, but there are some, inside that volume of liquid xenon, there are some very thin wires which are used to basically shape the electric field and also to produce electroluminescent signals for the S2 signal. And here you can see basically the people who are just putting this together. These are some of the photomultiplier tubes I was mentioning. There's the light detectors. And then here you can see them being assembled into those two planes of photomultiplier tubes. So ultimately, what you see on the left is one of the light detectors, and then you see the backside of the other one on the right. So you can see the orange sort of coils of cable. That's the backside of the other array of photomultiplier tubes. And then those two arrays are then flipped around and put inside the volume of liquid xenon to read out light. This is the detector being assembled. So now you can see the top photomultiplier tubes at the top of the picture. You see the circles, those are the front faces of the photomultiplier tubes. And this is now the thing being lowered down to form effectively the pot of liquid xenon that will be used inside LZ. Incidentally, you can see everything is done in ultra clean conditions, kind of cleanliness that typically you'd only see in the space industry or in semiconductor manufacturing, basically because we have to make sure that there is absolutely no radioactive contamination that can get into the detector, the experiment, for instance, from dust. And here is the constructed experiment just before it's put inside its cryostat. So it's basically insulated like a thermos flask, basically, from the liquid xenon. So this is what goes inside the detector. You can see an array of photomultiplier tubes at the top and another one at the bottom, and then this cylindrical shape is the outside of the volume of liquid xenon. So this is then that being packaged up, ready to be put inside the experiment. And here you see we're now underground. This is inside the water tank. And what you see here is one of the cryostats, one of the thermos flasks, in which we assemble the full experiment. And that's the thing that will basically keep the liquid xenon cold. Here you see the inner volume of the experiment being lowered into the outer cryostat. So this is effectively putting the innards inside the thermos flask. And this is one of the big tanks of liquid scintillator, which is what goes to make up the, what I said earlier, the Veto Detector, the gadolinium loaded liquid scintillator detector, with one of my collaborators for scale standing next to it. And then here you see the inside of the water tank. Now it's got the detector lowered inside it, which is sort of, you can't really see it, but it's sort of in the middle. You can see just about there's a white cylindrical shape. Everything's been coated in something called Tyvek, which is a very reflective material, so that we can record any flashes of scintillation light which come from the Veto Detector. The Veto Detector is the sort of plastic cylinder that you can see in the middle, and then you see the photomultiplier tubes that record the Veto signals. There's the sort of little orange blisters that you see all around the center of the experiment. Okay, so that's LZ, that's Lux Zeppelin. So what are we seeing? Well, we did our first science run last year, and we ran for 60 live days, as it's called, so basically 60 days worth of data taking. And if you think back to the diagram I showed you earlier, where I showed you the S2 size of the S2 signal plotted against the size of the S1 signal, I said that if you see a signal that is, maybe I'll scroll back to the diagram, probably get out quickly enough. There we go. So if we were in the orange region here, then that's where nuclear recoils and hence possibly the interaction of dark matter particles might sit in that orange region. whereas the blue region, that's background, that stuff which is nothing to do with dark matter, is probably just due to natural radioactivity. So what do we see in those 60 days worth of data? Well, the black points are the actual recoils that we observed. And you see they mostly lie in this grey region, which is basically that electron recoil region I showed you earlier. The purple region is where we would expect dark matter-induced nuclear recoils to lie. And basically the black points are largely in the grey region. So unfortunately, we haven't seen evidence for dark matter in that 60 days worth of data. So we didn't discover dark matter. This was in June last year. However, the data that you're seeing there is actually the world's most sensitive search for dark matter. So this is set, even though we didn't see any signal, we can now set very stringent constraints on the properties of dark matter. Interestingly, another thing that we can do with liquid xenon, I mentioned this idea of fiducialization, where you can measure the location of each recoil inside the detector. That's really useful, actually, and this diagram hopefully illustrates that. What you're seeing here, this is a representation of the location of every recoil event in that data set on the previous slide. So all the black points on here, this is then plotted in S1 and S2. We can also plot them in terms of X, Y, and Z, location. Z is along the Y-axis, vertical axis, and basically it's not actually X and Y, it's actually the radial distance out from the center of the cylinder we're plotting along the X-axis, the horizontal axis. And interestingly, what you can see is that if you look at the right-hand side of this diagram, you can see that the vast majority of the recoils are actually at the edges, at the outer edge of the liquid xenon, at large radius or at high Z. So at the top of the experiment or at the outer most edge. And the reason for that is because there is still some radioactivity, even after all the measures we've taken, there's still some radioactivity in the experiment. But most of the external radioactivity, it's mostly gamma rays, which generate electron recoils, is absorbed in the outermost layer of the liquid xenon. So because we can locate the recoils, we can just throw away all the recoils which are in the outermost layers of the xenon, because they're most likely to be background. So all that's left are the black points that you see in the middle here, and those are the ones that are plotted on the previous slide. And that's quite a neat idea that we can, that liquid xenon allows us to do. Now this is a bit of an abstract plot, but this is this is the money plot. This is the plot which really shows how powerful the experiment is. So this is when you do a lot of statistics with the data that I've just shown you, you can constrain some properties of the dark matter particles, given that you're not seeing any evidence for a nuclear recoil signal. And what you see here, plotted on the horizontal axis, is the mass of the dark matter particle, the mass of the WIMP. And on the vertical axis is something called the cross-section, which is basically a measurement of how strongly a dark matter particle interacts with an atomic nucleus, or in this case, a nucleon, a proton, or a neutron. These are important parameters because they are predicted by particular theories of dark matter. So if I was a theorist and I came out with a theory for a new dark matter particle, I could predict what the mass is and what the cross-section is. And I could predict a point on this diagram. And what LZ is saying is that if that point lies above the black curve, then it's not a valid theory. We've excluded it, because if it had been there, we would have seen a signal. And the fact we haven't seen a signal means that any theory above that black curve is not correct. So the only theories that are left are the ones that are below the black curve. And you see the other colored curves are from previous dark matter experiments. And as you can see, LZ is doing better than all of them. So LZ is currently the world's most sensitive dark matter search. Okay, so just to say dark matter searches have been direct dark matter searches have been going on for a long time. Earliest ones were in the late 80s, and as time has gone by, you can see that the constraints or the limits on this cross section have got better and better and better. If you follow the line, the arrows down to the right, bottom right, you can see that we've been getting more and more sensitive. Now we're down at, we have results from LZ. And in fact, there are follow-up experiments. So LZ will carry on running probably for another 5 years. So the results will get much better over that period. But even after that, then there will be other experiments. And in particular, we are proposing a new experiment currently called by the sort of fancy name XLZD. Don't ask me why it's called that, but there's an experiment called XLZD, which we are now proposing as the follow-up experiment after LZ, which will really be the ultimate WIMP dark matter experiment. And that might be operating in the early 2030s. So after 5 years of running of LZ, that might be the next thing that comes along. And so I'm involved in thinking about that at the moment. Okay, so what's the time? It's yeah. So I can say just last sort of 5-10 minutes. I can just say a few words about one other way that we can search for dark matter, which is to look for the production of dark matter in a particle collider. So this is a completely different way of looking for dark matter. And I'm talking about the Large Hadron Collider at CERN, which is the European Laboratory for Particle Physics in Geneva. So the picture you can see here is a picture of the LHC, the Large Hadron Collider, inside its tunnel. It's about 100 meters underneath Geneva. And this is basically a huge particle accelerator. And it's actually the world's largest machine. It's 27 kilometers in circumference. And inside the LHC, we accelerate protons, so that's the nuclei of hydrogen atoms, with radio waves. Basically, they surf on radio waves around the machine. And then we use superconducting magnets, which are the blue things you can see in the picture on the previous slide and in the bottom left here. Those superconducting magnets bend the beams of protons into circular orbit. In the right-hand figure, you can sort of see, drawn onto an aerial photo, you can see the sort of the layout of the LHC. You can see that compared with the runway of Geneva Airport, which is a major international airport. That really goes to show how very, very big the LHC is. Now, in the LHC, we collide beams of protons at 4 locations around that 27-kilometer ring. And in the collisions, the energy of the protons gets turned into the mass of new particles through E equals mc squared, so through Einstein's theory of relativity. And we build experiments around the collision points to sort of sift through the subatomic debris and understand what happened at the moment of the collision. And it could be, if we've got enough energy, it could be that we can produce new particles, genuinely new particles never seen before in those collisions. So it's like creating mini Big Bangs, actually. We're recreating the conditions in the very early universe. And it's actually through this process that we discovered the Higgs boson in 2012, so just over 10 years ago, 11 years ago now, which is the origin of the mass of all known fundamental particles in the universe. So that was a big discovery at CERN with the LHC. But equally, we could produce other particles that haven't been seen before. And one possibility is we might produce dark matter particles, we might produce WIMPs. So how do we go about doing that? Well, all of the experiments at the LHC have a similar structure. I don't have time to go into the details of this, but they basically all look like a Swiss roll. They look cylindrical, and the layers of the Swiss roll each carry out a different task. So there are particles that are created in the collisions that go flying out through the detector, through the layers of the Swiss roll, and they interact in different ways in the different layers. And by comparing how they interact in the different layers, we can determine what sort of particles they are. That's very important because that helps us to understand what those particles are. And if there are some genuinely new particles that have been created, they may only live for a fraction of a moment, or a fraction of a second. They might not make it out through the detector, but by understanding what they've turned into, if they've decayed into other stuff, then we can perhaps understand if there were any new particles created in the collisions. So that's just to explain the structure of a typical experiment at the LHC. It looks like a Swiss roll with different layers. And here's one. It's called Atlas. You can see two people for scale. This is on a much bigger scale than LZ. This is 45 meters long, something like 24 meters in diameter. And you can sort of see the cylindrical structure here. Each of the layers you can see in these cylinders are the layers of the Swiss roll I was just talking about. And the protons come in at either end of the cylinder, and they collide right at the very center in the middle. And here's a few pictures of Atlas being built. Don't forget, this is all happening in a cavern 80 meters under Geneva. It's a huge scale. And this is a picture actually of Atlas when it's almost finished, almost completely built. And you may just be able to make out there's a person to scale down at the bottom of the picture, standing, there's a sort of shadow standing sort of almost in the center at the bottom of the picture. That sets the scale for this huge experiment. So the purpose of all the layers of this Swiss roll, all the equipment in this experiment, is to understand what particles have been created in the collisions between the protons in the center of Atlas. So why is this relevant to what I've been talking about? Well, it's possible that if the collisions are of sufficiently high energy, then we could create dark matter particles. And what happens then is that some of the constituents of the protons collide with each other, so they typically quarks or gluons, as we call them, and they can collide and create dark matter particles. And what we can do is look in the sort of, imagine I've taken my Swiss roll and I've sliced vertically down through it. We can look sort of at what's happening in the collision projected onto that plane sliced vertically down through the Swiss roll. And if we've produced dark matter particles, what will happen is that some of those dark matter particles will carry away some momentum. And it'll leave what's effectively an imbalance in momentum, or it's called missing transverse energy. And if you look in the bottom right-hand diagram here, this is a representation of one collision in Atlas from the LHC. And what you can see here, the yellow bar is some energy or momentum carried by some visible particles. In this case, it's a very high energy photon particle. But you can see it's just pointing in one direction, and that means there's an imbalance in the momentum. That imbalance is represented by the red dashed line. Why is there an imbalance? It's because potentially a dark matter particle or two dark matter particles have been created, and they've carried away that momentum represented by the red dashed line. And that's a signature for dark matter production, missing transverse energy in the LHC. And the LHC might be a dark matter particle factory.
Okay.
So here's some real data taken, not sure exactly when it was, I can't, 2017, I can't actually see on my Zoom screen. And what you're seeing here, again, this is a representation of the data in Atlas. The big sort of blocks that you can see in yellow and green, they represent some visible particles that have interacted in Atlas. It's actually called a jet of particles. I don't have time to go into the detailed subatomic physics of that, but it's a jet of particles which is visible. But you can see that the jet of particles goes off in one direction and there's nothing balancing it in the opposite direction. So that means there's a lot of missing transverse energy in this collision, represented by the red dotted line. And that's a possible collision where we've created some dark matter particles. Now, unfortunately, there are other processes, just as in LZ, there are other processes, other background processes, which can mimic the signature for dark matter production in Atlas. And in this diagram here, you can see the latest results from Atlas in one of the searches for dark matter that we carry out. The data points in the left-hand figure represent what we've observed. So these are basically collisions that have occurred and been measured in Atlas. And then the histograms that you can see of the different colors, they represent more mundane, well understood physics, which can mimic that missing transverse energy signature that we've just been looking at. They're nothing to do with dark matter, but they produce the missing transverse energy signature. The most common process, incidentally, is the red one, the red histogram. And that's where we've produced an elementary particle called a Z boson, and that's decayed into two neutrinos. And neutrinos are well understood particles that are neutral, weakly interacting, and therefore mimic the dark matter signature, even though they're not actually dark matter themselves. So if you compare the black points in the left-hand figure with the histogram, you can see basically they sit on top of each other. So that again tells us we haven't seen any dark matter in that particular search. Interestingly, we can reinterpret the results of that in that plane that we were talking about earlier for the LZ experiment, and that's what you see on the right-hand figure. You see the mass of the dark matter particle on the x-axis, the cross-section on the y-axis, just as we had before. And what you can see here is that you've got results from direct dark matter searches, which is sort of in pink and blue. LZ isn't there because the LZ results are a bit more recent than this. But the results from the LHC are in yellow. So you can see that they're not as good as the direct searches at high mass, but they're actually better at low mass. So they're basically complementary to each other. And so it's an alternative way of searching for dark matter, but you're looking for the production of dark matter rather than the interaction of sort of cosmologically produced dark matter from the Big Bang. Okay, so I'll wrap up there. So just to summarize, dark matter searches, it's a really major area of physics these days. It was a bit of a niche area 40 years ago, but it's now, there are many hundreds or thousands of physicists working on dark matter searches and on the theory of dark matter. There's a huge number of different dark matter candidate particles. I've just discussed one in this talk. But you can see various possibilities over on the right-hand diagram. Lots of opportunities for innovation in designing new experiments. Some of them are actually relatively cheap by the scale of fundamental physics. But potentially the scientific payoff is immense, of course, because if we found a signal from either in a collider or in a direct search experiment, that would tell us something fundamental about our universe. It would basically tell us what 26% of our universe is made of. So it's a really exciting area, and the search continues. We'll stop there.
Okay, well, I'm going to risk trying to talk. Laura, can you advise me if the audio is coming through okay?
Yeah, it's coming through there okay.
Okay, so far so good. My apologies for my audio earlier. I'm on a sort of wireless link, and bad weather seems to affect us. These thunderstorms, they doesn't seem to help, but we've relocated everything. Hopefully I haven't broken up. I've just been waffling there for the last few seconds. So Laura can tell me, did any of those words break up?
No.
Good. Well, look, I'm going to briefly tell you about what to see in the sky and the big Venus watch that we have coming up at the end of this month for something really unique. We've never done it before. It's extremely rare. Do hold on for that. But I'm going to invite Dan to take a few questions. We normally ask people to pop them into chat. Unfortunately, I've wiped my chat now, having to log out and log back in again. So Dan, can you see the chat box yourself there? There was one question
yes.
I saw early on.
Yeah, I can. I can see that they already have a question from Glenn. So Glenn asks, if dark energy is the largest component of the universe, isn't it the bigger question to talk about? That's a very good question, actually. Yes, I think if you ask particle physicists, they would love to understand what the composition of dark energy is, just as much as they would love to understand the composition of dark matter. The difficulty is that dark energy is a very different beast. Dark matter, we think, is in the form of an elementary particle, from the arguments that I gave earlier on. That means it's amenable to sort of the kind of experiments I've just been talking about. So we could potentially understand its nature with experiments that we can carry out. So we could see the interaction of a dark matter particle with, say, a xenon nucleus. The difficulty with dark energy is that it's more like a sort of a universal force field, which is causing the universe to expand more rapidly. It undoubtedly is in the form of some kind of particle, but the mass of that particle is such that it's more like a field that basically the energy scale of dark energy is way away from anything that we could ever hope to detect directly on Earth. So what the best we can do with dark energy is actually try to understand what its sort of effect on visible matter in the universe is. So looking at the expansion of the universe, and in fact, if you've heard anything about the Euclid satellite, for instance, that launched just last week, I think it was, that's something which will tell us something about dark energy, but it won't actually tell us what sort of particle it is. It'll just tell us what general properties it has. And so basically understanding dark energy is a much harder problem than dark matter. And I think we generally think that we would be lucky to actually see get a direct identity for it. Okay. And then John has a question. I was wondering, are there any theories of cold dark matter behaving as a Bose-Einstein condensate and being detected as such, rather than a single particle creating a recoil, essentially like a cloud creating a series of recoils? That's also a very good question. So yes, actually, it very much depends on the mass of the dark particles. I've been talking about quite heavy dark matter particles. If I go back to my, I can scroll back to my diagram of candidates. We'll get my launch now. There we go, that one. So I've been looking at the right-hand end of this energy scale. Now, if you get to very light dark matter particles, then indeed they can start to have strange properties. They can behave like a wave. And so indeed there are, I mean, I'm not a theorist, so I wouldn't pretend to be able to give you a lot of information about how it interacts, but certainly at the low mass end of dark matter candidates, there are some weird things which can occur, which, for instance, you can look for a wave interaction in very sensitive atomic interferometers. So effectively, you could find evidence for dark matter using similar technology to what's already been used to find evidence for gravitational waves. So there are there are possibilities there, but that's not my area of expertise, I confess. Okay. Could dark matter explain the differences in the measurements of the Hubble constant? I'm not a cosmologist, but I doubt it. And the reason I say that is because dark matter is a even if we don't understand what it is, we understand very well what its sort of impact on the universe is in the observational universe. So that's basically baked into all the theories of cosmology already. So I don't think that would resolve the Hubble tension. I think that's already well, in some respects, dark matter is already well understood physics, even if we don't know what it is. Okay. Is there a Xenon detector in operation on the England-Wales border in the disused coal mine? No, there's not, but it's interesting you should say that, because I mentioned the XLZD project, which is a potential future dark matter experiment. So there are various possibilities for where that experiment might be located. One of them is the home state mine, which is where LZ is located in the US. But another realistic possibility is a mine in the UK. It's actually in North Yorkshire on the coast near Whitby in the Yorkshire on the Yorkshire coastline. It's called the Bulby Mine, and that was actually where some of the earliest dark matter searches were carried out. So it's a working salt mine, and it may be actually where XLZD was built. It'd be great if that were the case. It obviously takes money, so that's still to be agreed. But yeah, there could be basically the world's largest dark matter experiment, and the most sensitive, may be operated in the Bulby Mine in North Yorkshire in the early 2030s. Okay.
That might be it, Dan, for questions.
Sorry?
That might be it for questions, I think.
Is it? I've got one here from Thomas Finnegan.
Oh, yes.
Do you find it difficult to keep up enthusiasm when getting negative results? Or is there renewed excitement each time with a new search idea? So I should say, my career, I've worked on, I did my PhD on dark matter searches, actually at the Bulby Mine, so where I mentioned earlier on. I then worked for 25 years on the Atlas experiment at the LHC, searching for one particular class of dark matter particle, one particular class of WIMP, actually, predicted by a theory called supersymmetry. We still haven't seen any signal in any of these experiments yet, but as we set more stringent limits, we are, if you like, as we get closer to excluding the sort of regions of parameter space predicted by various theories, I'm an optimist. I tend to think that means that we stand a better and better chance of actually finding a signal. So I don't have any problem keeping up enthusiasm. If I did, I wouldn't still be in the game I am. So I've spent my whole career doing this, and I'm sure I will carry on doing it.
That sounds like a great place to leave it, Dan.
Yeah. Okay.
Keep up the enthusiasm, and thank you very much for your talk. Unfortunately, I missed the start, but the great news is we've been recording it, so I'll be watching it later on. And I just want to tell people briefly about what to see in the sky, the events that are coming up. If you have to rush off, please do it. My apologies for my bad link today. Hopefully we won't organise thunderstorms if you talk